Okay, everybody, so let's get started. So it's the EIP seminar, but we also have the Machine Learning Conference this week. We're very happy to introduce for the EIP seminar today, Helena Domínguez Sánchez. And Helena did her PhD in Bologna. And so the question I want to ask you is, have you eaten a trattoria datoni on Rio Gesturigi? Do you remember?
The trattoria?
Trattoria datoni on Via Gesturigi.
I was more from Osteria dell'Orsa, was my favorite.
Yeah, because I used to live above that trattoria. Okay, so, and currently, well, you sent me your bio, which is very...
It's too long, I know.
It's very long, yeah, but so I guess the interesting thing for people at EIP is that now you're currently at CEFCA in Teruel, which is very nice. Has anyone been to Teruel? It's a lovely place to visit. Helena tells me they have too many tourists, which is hard to believe, but it's a lovely place. And I'm very much looking forward to your talk today, which covers a lot of the themes that were in our machine learning conference. So, oh yes, one other important point. We'll be going to the restaurants that I've reserved nearby with the speaker. There's still a few spots available, so please come and talk to me at the end of the presentation. So, Helena, please go ahead.
Okay. Thank you very much. It's a pleasure to be here giving the EIP Colloquium seminar, and it's even more to be in this beautiful room with this professional setup. I prepared this talk as an EIP Colloquium, so for a broad audience. So for the people attending the machine learning seminar, most of these things may be basics for you. I'm sorry about that, but I didn't want to change the audience. I'm going to talk about what I've been interested in deep learning in the last few years, which is for galaxy morphology or classification of galaxy images more broadly. And this is the list of collaborators, and the order is not random, it's just decreasing in size. And I like this picture because it shows an oak. I'm from Salamanca. Oaks are very common there, and it's a beautiful image with a beautiful galaxy. What can you expect about this talk? I will try to convince you that we care about galaxy morphology, why deep learning is the correct tool to measure it. I will focus then on a big part of my work, which is supervised deep learning, in particular convolutional neural networks. But because you need labels for that, then I will go to what happens if you don't have labels. And I will explain a little bit different techniques like transfer learning, the use of emulations, or unsupervised learning. And I'll end up with a new project that I'm working on, which is about going deeper in the universe. So why do we care about galaxy morphology? If you look at the sky, most of you know this picture very well. But one thing that strikes at first is that there are many, many galaxies, and they're very different. They not only have different colors, they have different shapes. They have different sizes. Some of them have beautiful spiral arms, like this one here. Some of them are just round and red, right? So because we know they have different shapes, it's a good point to measure that. And already in the early century, Hubble realized that there was a transition in this galaxy morphology, which is known since then as the Hubble classification scheme, where basically you have two main groups, one which you could call the early type galaxies, which are round, where they're elliptical, smooth, and with reddish colors with no features at all. And then you have the late type galaxies, which start having very nice spiral arms. They have more importance of the bulge component as we move from the left to the right. Some of them can have a bar in their centers, which are the ones down here. And then there's a third group, which are the irregular ones, which don't have well-determined shapes. And in between, there is this transition group, which are called the lenticular galaxies, which they have a disk and a bulge, but they don't have spiral arms. If you order this sequence, you will get what we call the T-type, where T-type below 0 usually corresponds to elliptical galaxies, and T-type above 0 usually corresponds to spiral galaxies. And as you go to higher values, they will have more spiral arms and bulge component. The funny thing is that when you look at these shapes, they are very much correlated to intrinsic properties. For example, spiral galaxies are intermediate and low-mass galaxies with young stellar populations because they're still forming stars in the spiral arms, and they are supported by rotational velocity. And on the other hand, most of the elliptical galaxies are dead objects that stopped forming stars a long time ago and have evolved passively since then. They're the most massive objects in the local universe, and they're kinematically dominated by velocity dispersions. So indeed, this morphology relates to fundamental galaxy properties, and we can see that from this cartoon, where it's shown here is the star formation rate, is the number of stars per year that a galaxy forms, versus its total stellar mass. And you can see that there is a nice relation here, which is called the main sequence, where galaxies have a star formation rate proportional to their mass. And this main sequence is mostly populated by spiral galaxies. And for galaxies that have lower star formation rate as expected by their mass, these are mostly elliptical galaxies, very round galaxies with an important bulge component. And here, this cartoon also highlights that there are some fast rotators and there are slow rotators. And most of the spiral galaxies are fast rotators, but there are also some elliptical fast rotator galaxies that was recently discovered thanks to IFU observations. We can do this plot with real data. Here, as a proxy of the morphology, the plot uses the Sersic index, which is a measurement of the light profile concentration. So basically, low Sersic index is a proxy for spiral, high Sersic index is a proxy for ellipticals. And you can see here again the star formation rate mass plane. One thing that comes out to your mind is this very straight relation is the main sequence populated by spiral galaxies, and then you have the red sequence populated by elliptical galaxies. And this has existed already since redshift above around 2. You already see this relation, and there were already quenched galaxies as long time ago as redshift 2. What we want to understand is how these morphological transformations have changed across time and how this is related to their capacity for forming stars. And this is summarized in this very complex plot where what is shown is the star formation rate density, so the capacity of forming stars per arcsec versus the age of the universe, or redshift if you prefer, for all the galaxies, for the star-forming ones, and for the passives. So I want you to focus for the star-forming galaxies. At the very beginning, most of the contribution for the star formation was in irregular galaxies, which was then mostly transformed into spiral galaxies. On the other hand, the passive galaxies, the star formation rate density is mostly contained in bulge galaxies. These are spheroids or displaced spheroids. So there is a clear connection between having a bulge and being quenched. But we don't really understand what causes what. Is the morphological transformation that quenches the star formation, or is the other way around? And therefore, this is a very open question. It's crucial for our understanding of the universe to have large and accurate morphological classifications of galaxies to tackle this issue. So, as you can imagine, one way to classify galaxies morphologically is to check the images one by one. But as most of you know, upcoming surveys will observe billions of galaxies, so this is completely impossible task. And therefore, machine learning, and in particular deep learning, is a very practical tool. It has been applied to many different tasks through the last 10 years with a lot of success. And in particular, deep learning is optimized for image analysis, and galaxies can be seen as images. So it's and the classification problem of cats and dogs is very similar to the classification problem of elliptical spiral. Here, there's a plot that I just grabbed from the internet yesterday. I even forgot to say that, to remove the download data in CBS. But basically, you can see how this is the number of papers with the word convolution, which is a proxy for deep learning, in the last 10 years. And you can see how this has exploded, especially after 2018. So as people from the conference know, deep learning has matured a lot, and now it has started being normalized as a tool for astronomy. And in particular, I think that one of the greatest successes for classification of galaxy images. So for those of you who are not familiar with deep learning, what do we mean by deep learning? First, let's try to understand what is a neural network. A neural network is nothing else but a very complex mathematical function, okay? Basically, you have an input, which could be a vector of n dimensions, and then it goes through this kind of hidden layers, which will do some mathematical transformations that I will explain now, and basically gives you an output of n dimensions where the output dimensions usually is smaller than the input dimensions. So what are these mathematical operations? For each of these neurons in the hidden layer, so let's take this one, it will receive the input, all the inputs, okay? So this neuron is connected with all of the previous ones, and it will be connected with a set of weights, which will be summed up and then activated with a function, which can be a sigmod or whatever. And this propagates all over up to the end. So basically, this is just a mathematical function. You have an input, do some maths, and get an output. The nice thing about this is that how you optimize this function, okay? You want to minimize your loss, where your loss is basically the difference between your input and your output, and you can use a loss like a binary cross entropy. And you do that through gradient descent. So you do a first random number of weights and measure your value. Then you shift a little bit your weights to one direction, and you compute again your loss. If it's smaller, then you moved in the right direction. So you take a step in that direction again. If your weights are larger, then you change direction. And this is what is called gradient descent, and it's how you can optimize your loss function, and you train for different epochs. And this is basically how a neural network works. What is a convolutional neural network? Well, the first part, the last part is the same, but before that, there is a convolutional part where basically your input is not a vector now, but it's an array, and you convolve it with different filters. So these are the effect of convolving the number 6 with different filters, and at the end you flatten all these numbers, so basically you just convert an array into a vector, and then you start doing your neural network operations until you get one value which is more probable than the others. In this case, successfully is the number 6. And one thing that I want to clarify is that the weights of these convolutions are learned by the machine. Okay, so deep learning has exploded. Here are a number of references. If your name is not here, blame Marc Huertas, because I borrowed this from his talk last week. And as you can see, I'm not going to refer to all these papers, but I'm going to focus on my 2 papers, which were relatively pioneers in the sense, for example, that were the first one to publish a catalog based on deep learning, and also one of the first to use transfer learning in astronomy. Okay, so I'm going to focus now on this work, supervised learning using convolutional neural networks. Because it's supervised, you need a data set that has been previously classified because you need your labels. Thankfully, we had the Sloan Digital Sky Survey, which has sampled one-third of the sky with a 2.5-meter telescope. And we counted at the time of the paper with 2 catalogues. One's the Galaxies 2 catalog that includes classifications of 240,000 galaxies, and it's based on a classification scheme where, where basically you can see that the users, because this is a citizens science project, are asked some questions, and depending on their answers, they move through a decision tree, and then you have a catalog of different classifications for different galaxies. And then there is the Nair and Abraham catalog, which is much smaller, only 14,000 galaxies, but it's much more detailed, and it's done by professional astronomers. It includes a T-type, so the sequence that I showed you before, and it also includes the bars, rings, etc. So this is the architecture of the neural network that we use. The input is an array of 69 times 69 pixels, where the cutout is proportional to the size of the galaxy. So the galaxy occupies more or less the same region independent of its distance or its intrinsic size. Then there is this, and the flux is normalized. And we don't want, it's normalized removing the color information. So we are removing any color and any size information in this project. And you can see, so here are the number of weights. So you start with 3,000 weights, but when you move through this complex neural network, the number of free parameters of this equation is 2 million, right? But that is why it's so successful, and that is also why it needs a lot of training sample. The classification scheme that we designed was the following. First, we have a model that separates elliptical from late type galaxies. It's a binary classification. Within them, we also separate ellipticals from lenticulars, and we identify barred and edge-on galaxies. And you can see some cutouts here color-coded according to their class. And there's also a regression model that returns the T-type. Okay, so you have the binary classification and a regression model. And in the paper in 2022, we refined the models that we developed in 2019 by, for example, determining better the T-type, including the early type, late type model, and also including an uncertainty estimation and a visual classification. The fact that the T-type is, so here you can see the output. This is the predicted T-type versus the input T-type from the Nair catalog. And you can see for the new catalog is the red line. There's a very, very nice correlation. Of course, it breaks up a little bit at the end because there are very few galaxies with such high T-types. And here you have the comparison between the early type, galaxies classified as early type and late type by the binary classification, and their T-type also according to our own model. So you can see that while there are no late type galaxies with T-type below 0, there's a tail of early type galaxies with T-type greater than 0, and I'll go back to them in a few slides. We also did binary classifications like the detection of edge-on galaxies and bars. This is a ROC curve that represents the true positive rate versus false positive rate. So you want this value to be high and this one to be low, like the green curve, which is what we obtain for the edge-on galaxies with certain values. And what I mean by certain is that their uncertainties are within below the 1 sigma distribution, and the uncertainties are derived by doing a cuff-fold. This means that we train 5 separate models by varying a little bit the validation and the training sample. So you have variations on the initialization of weights and on your training sample, and that gives you different probabilities, and you can combine them to determine uncertainties. And the fact that these uncertainties are meaningful is reflected by the fact that this ROC curve works much better for the certain galaxies than for the uncertain galaxies. But on average, the accuracy is great. We get a 98% of accuracy for the edge-on galaxies and a 93% for the bar galaxies, which is pretty good because detecting a bar is not a trivial task. Okay, so In the paper of 2022, we applied the sample to the MaNGA sample, which consists only of 10,000 galaxies, so only we were able to visually classify all of them. And this is the comparison of our visual classification with respect to the T-type, so you see there's a very nice correlation. And we also set a flag if our visual classification was reliable, because even by eye, sometimes you don't know what you're detecting. So you can see how this reliable classification really drops at the intermediate T-types, which are the most difficult ones to assign a category. And I also said that there are some galaxies that are classified as early type, but have T-type above 0. Okay, what are these galaxies? They are galaxies which are small, faint, and have very low velocity and have a low velocity dispersion. So they're consistent with galaxies being disk-like, but being too faint to show a clear spiral structure, or also fuzzy irregulars. We also compared our results with the Galaxy Zoo. The first question of the Galaxy Zoo is not, is the galaxy elliptical or spiral, but is the galaxy smooth, or does it show features? So you can see that if we plot our classification versus the probability of being smooth for the Galaxy Zoo, there's a non-negligible fraction of galaxies which are smooth, but according to our classification, they are spirals. And if you look at the distribution in Sersic index or B over T of these galaxies, they have low Sersic index and they have a low B over T, so they're more consistent with being disks. So being smooth is not equivalent of being elliptical. It means the features are unclear. So what we did with all these classification, we published it in the shape of different catalogs. We did one containing 6,000 galaxies for the SDSS data. And we also, in 2 different versions, you can access the latest version here. And we also published the MaNGA catalog in different versions with its companion pi-more photometric catalog, which provides photometric fits like Sersic index, B over T, radius, etc. And I mentioned before MaNGA, but I didn't explain what it is. It's a survey that is an IFU survey, so for each galaxy you have many fibers and you can derive a spectra in different locations, so you will get 2D maps of things like H-alpha, rotation, dispersion, etc. So we have not only published the catalogs, but we have used them for science. Remember this cartoon? Now we can do it with real data. This is the star formation rate versus mass color-coded according to our T-type. And you can see that there is a very nice transition of colors where you have most of your late types in the already quenched. You have your high T-type galaxies being low mass star-forming galaxies, and you have your quenched galaxies being intermediate types. So there's a very nice sequence here. We can also check how the morphology relates to kinematics. This is a very common plot showing the angular momentum. It's a measurement of the rotation, so high rotation, low rotation versus ellipticity. And this corner here shows the location of slow rotators. The 3 panels just show galaxies that are better fit by 1 component, 2 components, or equally probable. But what I want you to focus is how well the elliptical galaxies populate the slow rotating region, while on the other hand, the late type galaxies are very fast rotating, and you have the lenticular galaxies on the fast rotating region. And of course, I don't have time to go into the details. We did a long series of papers where, taking advantage of the morphological classification, we studied the stellar population gradients. In this case, I'm showing age, metallicity, alpha enhancement, and mass to light ratio versus radius. So this is the center of the galaxy, this is the outskirts. And here I'm highlighting the difference between fast rotating ellipticals and lenticulars. And there are clear differences between their stellar populations, suggesting that they're not the same objects as other authors in the literature proposed. Okay, So far so good. Things work very well, but that was because we had a great training sample, a very large training set. What happens if you don't have labels? For example, when the dark energy survey came, there were very little overlap with the previous morphological catalogs, so we could not apply the CNNs as we did in previous works. So our question was, how much of the knowledge learned from the SSD images is useful for the dark energy survey? And we did this test where we basically, so again, this is the ROC curve. You want your data points to be up here in the corner. And this is for the classification smooth and disk. The blue line is the results that we obtained for the previous SDSS sample. If you take the models trained with SDSS images and apply them to dark energy sample, the performance is much worse because there are subtle differences in how the instrumental effects, PSF, pixel size, depth of the survey. So your machine learning code is not optimized for that data set. But if you, instead of start training from scratch, take your weights and then use only a few galaxies to adapt the neural network, which is called transfer learning, then you have this beautiful red curve using only 500 galaxies instead of 5,000. And we tested that for different questions. The results were very nice. And we demonstrated that recycling these weights can help you to reduce by 1 order of magnitude the size of your training sample. I'm, of course, not the only one who has done that. And in the machine learning conference, Mike Walmsley saw these very nice results where they obtained a similar thing for the Galaxy Zoo. And also an interesting thing is that if you train a model which is able to do all the tasks at the same time, then there is not much difference when frozen or not frozen, when you've trained the different layers. Okay, but still, the results I saw need around 500 galaxies labeled. What if you have no labels at all? Then you can use things like domain adaptation, when the trick here is that you have a set of data, and this, I'm taking this figure from Huerta's company 2023, who used this method to classify JWST galaxies. The idea here is that you have Candle's galaxies with classifications and Sears galaxies without classification. So first you have a classifier that will create a feature space which will be flattened and then will go through your classification. And this part is like the classifier that I've been showing before. But now you have a set of data that don't have labels. They go to the same feature structure, and then instead of going to the classifier, you go to a discriminator. And this discriminator needs to understand if the galaxy is a Sears or a Candle's one. And you want to cheat this discriminator. You want this parameter space to be so similar for the two data sets so that the discriminator won't be able to say the difference. So you penalize when this is clear, and you optimize when this classification is doing good. And there are many interesting works by Ciprianovic. You can see, for example, how before domain adaptation, the one data set and the other data set lay in different parts of the feature space. And when you do the domain adaptation, now they're clustered together, and it's difficult to distinguish them. Okay, so far, we've moved in the low redshift bright end regime. But if we really want to understand how the properties of galaxies have evolved with time, we need to go to higher redshift. And distant galaxies are more difficult to classify because they look fainter, smaller, and even more important, we don't even have catalogs to train those samples with. So, and here I want to highlight, for example, the catalogs that I used in the previous papers were limited to magnitude 17. And this is the distribution of magnitude for the dark energy survey. So you can see that it barely covers, what, 5% of the data? And we want to push higher, right? We want to be able to classify to higher magnitudes. So the idea we had was, okay, we have the original dark energy survey images, some of them with labels, because we could cross-match the dark energy survey with the SDSS catalog of 600,000 galaxies. Because we know how galaxies are affected by being more distant, let's emulate them. So we apply things like cosmological dimming, reducing the pixels, the size in pixels and the flags, also convolve with the correct PSF and noise, and even did a little bit of correction and evolution. And this is how the same galaxy looks like when you push it to higher redshift or fainter magnitudes. And this is the same. And the trick here was that we used these images, but we kept the original labels. So we fed the model with all these images saying, all these are spirals, all these are ellipticals. And we have excellent results. Here you can see, again, we trained 5 different models, and you can see that the accuracy is 97%, but also the precision and recall are very good, as you can see for the confusion matrix. And more importantly, we study if these models depend, if the results depend on the observed magnitude, and we didn't see any dependence. You may see a little bit of wiggling here, but please notice that the lower end here is 90%. So all of our values, precision, recall, accuracy, are above 22%, 92% for all magnitude ranges. So we demonstrated that machines can recover features which are somehow hidden to the human eye, because by eye it was very difficult to classify some of these galaxies. And to further test if our results were reliable, we made use of the Viper's spectral classification, which classifies galaxies into passive, intermediate, and star-forming according to their spectra. And you can see what a very nice correlation with our morphological classification there is, with a 97% of true positive, for example. So again, we applied all these models to 27 million galaxies in the dark energy survey, and we released the largest morphological catalog up to date, reaching magnitudes up to 21.5. So you may wonder, what happens when you apply models trained with only the bright end? And this is exactly what we tested when we compared our catalog with the catalog made by Cheng, in which they basically trained with the labels they had up to magnitude 17. And this is the comparison of their classification with our classification. And you can see that there's a very nice correlation, so you want this matrix to be diagonal, up to precisely magnitude 19, and then this relation completely breaks. And their model only predicts spiral galaxies. It's not able to identify elliptical galaxies. So don't train with a sample different to your target. Okay. So far, for everything that I showed, you need a little bit of labels. For some projects more, for some less. But what if you don't want to use any labels at all? This is what is known as unsupervised learning. And the idea is to let the algorithm find any underlying structure in the data. And you can see here a plot where galaxies are more or less ordered. You can see here the clear effect of the color, but also if you look at different regions, these galaxies look similar. You may need the data at some point to interpret your results, of course. But this is a good way to detect anomalies. And there are different flavors, so you can do clustering, dimensionality reduction, and contrastive learning. For example, you don't really need to do very fancy things. You can go to classical PCA, which is basically a dimensionality reduction, to try to summarize the immense amount of data that we have in the MaNGA survey. In this case, we're focusing in a series of papers by a PhD student, Josep Tous. We use the lenticular galaxies from MaNGA, constructed radial spectra. So for every 10 steps, in 10 steps of radii, we constructed different spectra. And we can project this spectra in the PC1, PC2 components and see how the radial profiles change in this PC1, PC2. We can summarize that information even more by vectorizing this, and because this is the passive region and this direction is towards more activity, then we can define activity gradients which are flat, which increase outside in or inside out. And we've done several studies that I don't have time to show you here, but just wanted to show the technique. There's also what is known as self-supervised machine learning, where basically your labels come because you're showing the same image with a little bit of a variation. So you take one image, you do some random shifts, but you tell to the encoder, okay, this is the same image, so put them together in your parameter space, and put any other image more distance to them. So at the end, you have a feature space that clusters together, that groups together things which are similar to each other. This is what we did in a paper by Regina Sarmiento in 2021, again using the MaNGA data. And as input, she used different maps, like flags, age, metallicity. And then to visualize the results using a new map and a clustering, what I want to highlight is that the three groups she found correlate very nicely with the classical morphological relation as the T-type, and also with the main sequence, the red sequence, and the green valley. And you can also do this with, for example, James Webb Galaxies. So these are a set of simulated JWST, and you can see how it correlates very well with CERSIC index. This is a work by Vega Ferrero. When you compare it with the real observations don't really lie in the same area as the simulation, so this is highlighting differences between the two samples. I don't want to tell you more about that because there's an interesting talk, it's a talk about this today at 3 p.m. for those who are in the machine learning conference. Okay, and I'm reaching to the last part of my talk in good time, so I'm going to take a moment to drink water.
We can take questions if you'd like.
Yeah, would you like any questions before we move on?
Yeah, well, I have a quick, I'm going to abuse my position as speaker. Can you just, it's great that you've made all these catalogues available. Can you make a comment about how you estimate the uncertainty on the morphological types in your catalogues?
Yeah, I didn't explain that very well. Basically, what we did was to train 5 different models, and these models have different values, so you can measure the deviation, the standard deviation of the output, and that is a proxy. It's not the best uncertainty estimation, but it is meaningful in the sense, do you remember when I showed the ROC curves? They work better for the ones that have smaller uncertainties. Okay. So we went to higher redshift. We tried to do things without labels, but now we want to go deeper. By deeper, I mean integrating more time, seeing what is in the outskirts of the galaxies. Because we know the hierarchical paradigm tells us that galaxies are not isolated bodies, that they suffer interactions all throughout their lives. And these interactions actually leave very nice remnants known as tidal features, tidal tails, shells, and so on. But these are invisible for shallow surveys like SDSS. So you can compare the same image using SDSS or a deeper survey. You can see that how all these tidal remnants become evident only when you integrate enough time. So in the paper that I'm going to present, we wanted to test if the CNNs were able to detect galaxies that had tidal features around them. So in principle, again, it's a classical cat and dog problem with images, should be easy. But there's a big problem. These features are very faint, and there are very few catalogues that have tidal features. And although there are ongoing efforts, like the one by Sola, and there was a pioneer attempt by Walmsley, but the accuracy was only 76% accuracy because look at the numbers, very, very small training sample. But these are, so what we did was to use the catalog by Garrett Martin, which is based on simulations. And the images were classified by professional astronomers in different types, like merged remnant, tidal tail, stellar stream, a shell. And what I did to convert those votes into classes was, if the fraction of votes divided by the number of classifiers is above 1, then it's a positive. If it's 0, then it's a negative, and if it's in between, I'm going to remove it from my sample because I don't know what is the class. And you can see here the effect of going fainter. So this is a galaxy observed at 36 magnitude per arcsec, while this is at 28 magnitude per arcsec. And I don't know if you can see it well, but basically the fraction of tidal here is 0.2, while the fraction of tidal here is 3. So how the votes of the classifiers change when you go to fainter magnitudes. And this is, again, the highlight. If the red ones show the distribution of the images which are classified as positives, and you see the great dependence with the depth of the image and with the redshift. So we did a little bit the same as what we did for the galaxy morphology. And here you can see that the accuracy now, it's smaller, it's only 85%, but because this is a much more challenging task, it's not as easy to separate ellipticals and spirals rather than to detect these features. And in addition, the training sample was small. We studied the dependence of our results with the different morphological classes, morphological in the sense of the tidal feature classes. So we were able to recover all the shells, and the mergers and the tails were the ones which were more difficult to be recovered. And of course, we also studied the metrics with respect to the depth of these images. And here I want you to see, this is the fraction of detected features by the classifiers. So there's a clear correlation between the deeper the images are, the more classifiers detect the features. Our accuracy and purity, which is the red line, are more or less stable throughout the full regime, but it's the completeness that is seriously affected. So if you want to have at least 90% completeness, you really need deep images to retrieve these things. We had real data coming from HSC, visually classified, so we tried to apply our models to that. And the performance was not good. We state that in the paper. We even tried transfer learning. It didn't work. And my intuition is that, first of all, the visual classification of this data are very uncertain. I want to highlight here that for the galaxies that are classified as detections, only 15% of them are classified as such by the 4 classifiers. So there's a lot of disagreement between the classification. It's not easy to say if there is a detection or not. Also, the data is much shallower. It's 26 magnitude. We were talking before simulations of 31. And the simulations are not completely realistic. They don't have exactly the same angular resolution. They don't have artifacts as sky subtraction, background sources. So this again highlights the fact that you have to be very careful when you train with simulations and apply to real data. And as Nabila was saying the other day in the conference, we need end-to-end simulations, like really take into account all the observational effects. So if we want to increase the statistics of tidal features and tidal tails that we observe, we need to do on-purpose surveys. And this is precisely the objective of ARRAKIHS, analysis of resolved remnants of accreted galaxies as a key instrument for halo surveys. I will never learn this name.
Because you guys read Dune.
Yeah, basically. So this is a new ESA mission approved in December, led by Spain. And I have also a leading role in some of the working packages and as PI of the Plan Nacional. And the idea is to sample 100 nearby galaxies to unprecedented depths, reaching 31 magnitudes, to study the nature of dark matter. You can see here how different flavors provide different number of satellite galaxies. Also to study stellar streams and diffuse light, and of course, what I'm interested in, galaxy mass assembly and mass accretion. So the telescope will be very simple. It's a binocular with 4 filters, 2 in the optical, 2 in the infrared, and will provide images observing these beautiful tails that we'll be able to study. So now, how can we use machine? And before I move on, as I said, I'm the coordinator of one of these packages, and we have 2 positions open at CEFCA, one as a software engineer and the other one as a postdoc working with me on applying machine learning techniques to the analysis of these images. So if you're looking for a job, don't hesitate to contact me. So what is the idea now? How can we use machine learning to study 100 galaxies? Do we really need machine learning? We need that because we can do segmentation. Instead of classification, the idea is to do segmentation. And we are doing tests with models like Segment Anything model, which is it's not open source, but you can, I think you can download the code and you can use it on the interface. And basically, you input an image. It doesn't matter the texture this image has, and it identifies the different segments. So of course, we can do this with galaxies too. And this is a very preliminary test where, again, using simulations at different magnitudes, we're trying to see what the segmentation recovers to optimize the depth we need to reach to not to lose any significant information. And I'm done. I'd like you to take some messages home. So deep learning is a very useful tool for classifying galaxy images, but you have to be careful with some things. Supervised deep learning needs large training samples that must be from the same domain, the magnitude range, the instrument, etc. Be careful with applying simulation-based models to real data. Always have a backup test so you can test that your results are right. We also demonstrated that there are some tasks for which the machines still have problems. For example, detecting the faint and subtle features like tidal interactions. This is still a challenge and an open problem for deep learning. We can overcome the lack of labels by using things like transfer learning, emulating galaxies, or using unsupervised learning. And finally, please do not blindly apply your models to data from different domains as the training sample, because can give you the wrong answers, sorry.
Thank you very much, Helena, for the very nice talk and lots of those wonderful results. And there's a question already from Gary. I'll just give him my microphone.
Thanks very much, Helena. Your work is very impressive. So I have 2 questions. One, you mentioned that when you do the morphological training, you don't use the color information, and indeed, people might not want you to use the color information so that they can see the effects of colors later. Or you could do it the other way and say, but maybe I can do better with the colors. And then when you compare to the experts, they were probably, or the Galaxies volunteers, they were probably biased by the colors they saw. So what do you think about that?
Yeah, that's a very nice point. I've discussed about this several times. I think we should focus, like the morphological classification is based on the shape, and it should not be biased with the color. If you give the color information, because most of your ellipticals will be red, then it will be more difficult for the model to classify as an elliptical something that looks bluish. Mm-hmm. And it may look bluish because there was a lack of a filter or something like that. But also, if we want to identify the outliers, so what I'm interested in is precisely in those galaxies which are transforming, mm-hmm. so that may be red but are still spirals, or the other way around. Mm-hmm. So if I'm adding the color information in my model, my prior is going to be affected and will give more weight it will be more, probably more easy to classify as an elliptical something that is red, when precisely if I want to study the color morphological relation, this has to be independently derived.
Thanks. And then another quick question is, I always thought that you need huge samples, and that's what you said in your conclusion, to train things. But in the end, you did do training. You did classify the Sloan galaxies, the 500,000 Sloan galaxies, with, and you measured T parameters, which were trained with the Nair sample of only 10,000 and not 1 million galaxies. So is that reliable?
Yeah, that's a very good point, and probably, if I can go back, of course, a training sample which is smaller than the full data set may not capture the full complexity. It's very far away.
Maybe I fell asleep after that.
This one, here, okay. So one of the problems, or one of the deficits of the, oops, oh, what happened? There, sorry. No. Oh my God, I'm sorry. I'm going back, oh no, sorry.
Always happens to me in talks.
Okay, there we go. So, well, I don't know if I can point, but anyway, you can see, so the points that the individual data points are individual galaxies. And you can see there is a lack of galaxies at T-type larger than 7, right? Why? Because these very late type galaxies are not frequent. So in a sample of 14,000 galaxies, there won't be many of them. So probably for this population, yeah, the T-type is not as well characterized as for others that there are more abundant galaxies.
But still, it's pretty good for the others.
Say it again?
But your work works pretty well for the non-irregular galaxies. For the lower T-types, it works very well.
Yeah, and if I have to be sincere, we did for the 10,000, not for the 6,000 galaxies, but for the 10,000 galaxies of MaNGA, we visually checked them, all of them. So, and the agreement, I have a backup slide, but it's not in the PDF. And the agreement with the visual classification is pretty impressive.
Yeah, thank you. There's a question in the back. Just introduce yourself.
Hi, Ben Giblin from Edinburgh. Thanks for the great talk. So if I understood correctly, the uncertainty on the classifications was approximated by the variation across the 5 different neural nets. So I hear about Bayesian neural nets, and which I think can output an uncertainty on the point estimate or point classification, as well as the classification itself. Would that have been possible to construct it that way in this case, and is there an advantage of doing it that way?
Yeah, indeed I tried doing that, but training a Bayesian neural network is more difficult because basically you have double parameters, right? You have a mu and a sigma for each weight instead of one weight. So the results, like the accuracy or the mean square error for the T-type were worst. And at that time, I prefer to have a more accurate value on the T-type, even though my uncertainties were not the statistically perfect uncertainties. But at the end, nobody uses the uncertainties. I mean, we are super worried about them. But if the users of the catalog, I think it's better to have a non-biased value than a better estimated uncertainty. But of course, you can do that with Bayesian neural networks.
Okay, there's another I think this. Say your name and.
Hi, I'm Jelle Mes from Leiden University, and I have a master's student actually also working on the detection of stellar streams. So I'm quite interested in that, and I was wondering, you mentioned that for morphological classification you would only want to use the intensity and not the colors. Mm-hmm. Would you use the same for the stellar streams, because you know that they're usually more red?
That's a good question. For this work, I only use one color band for the tidal stream detection, but probably for the ARRAKIHS work, I will definitely use the color information, I think, because it's giving you hints on how you can differentiate the background, foreground, and stellar streams. That's important. And because then we don't really want to study well, yes, of course you want to study colors, but it will not be as biased, it will be of much help, I think.
Thank you.
Yeah, there's a question there.
Yes, thanks for the talk, and apologies, I missed the beginning. So
Agnes Ferte.
Yeah, Agnes Ferte from Slack. So maybe you touched on that, but I've always wondered, because some effects on galaxies that are co-localized will have some effect, like for instance, they will align with the tidal fields or things like that. Can we take that into account when we train a neural network? And I'm thinking, like, my first thought would be to actually use large images rather than just cutouts. Does that make sense? Do you have any
That's
thoughts?
a good point. I didn't thought about it for the tidal tails, but on the opposite, I'm working on a project now for identifying membership of clusters of galaxies. And for that, we are using the full field of view, because the location in the cluster may be useful for identifying the cluster members there.
Thanks. Are there any more comments or questions? I have a quick comment. You didn't say very much in your talk about comparisons with simulations, or what physical processes you can infer from the morphologies. And I know there's a lot of work that has been done, and that's probably too much to talk about. But I wonder if you could say one or two words about how you go from morphology to an understanding of the physical processes in galaxy formation.
There's a project that I'm working on right now that I really like, and it's precisely to apply unsupervised learning to the star formation histories of galaxies from simulations. And I don't have the result here, but it's beautiful how the star formation histories clusters. And then you can, again, group your galaxies and see what is the outcome of those star formation histories, which kind of morphologies you get. Unfortunately, you can only do that with simulations, because to infer the star formation histories of these galaxies, it's another topic that also takes off my sleep sometimes. But yeah.
There's a question from here. Just say your name and who you're from.
Sure. Yeah. Hey, Luis Suelves from the NCBJ at Poland. So yeah, thank you very much for the very nice talk. So my question, it's a bit strange, but let's see if I can word it properly. So when you are working on finding the tidal structures, and there were basically bridges and tails were kind of getting a bit less easy to find, right? Have you seen because of course you analyzed how it was going with the depth of the survey, but because I had a feeling that maybe the reason why it's difficult to get it with SSC is the fact that you have so the brighter is the tidal structure, that means that also usually the brighter it is, also the bigger and the more resolved would it be, right? Mm-hmm. So would it be that the problem is coming from having just too many low resolution structures, sources, stars, tiny galaxies around, spoiling the image? Could that be one of the reasons?
Not in this case, because these are simplistic simulations that don't have background objects. Yeah. And indeed, at some point, we thought about including these background objects, but then the visual classification would have changed. So we left it for a follow-up. But what I can tell that I passed relatively quickly, but I think it's an important point. It seems like all the shells are being recovered, and it's the case. Now, I hope this pointer works. Yeah. So this is the output probability of the model, and this is the threshold to classify something as a stream or not, as a tidal feature. So you see that for all the shells, this probability is high. This means that we recover all the shells. But the fact is that all the shells are classified as other features. So all the images that have a shell, they also have a tidal tail, or they have a bridge, etc. So probably it's not that they're the easiest to identify, are the most evident, right? And because they're most evident, then you classify them more easily.
I see. Thank you.
Do you have some more comments? No questions on Slack, I guess, Guillaume. Okay, so while we're waiting, why is ARRAKIHS a binocular telescope? What does the binocular do for you exactly? There are 2 detectors in each of the binoculars?
There are 2
It's
binoculars.
2D? 3D?
It's 2 binoculars, 1 for each filter.
Okay. And the field of view of the telescope is how much?
The field, I don't remember now.
Okay.
Yeah, I'm bad with numbers.
Because there's another telescope that might be able to do some of that work as well. Have you thought about applying those techniques to that data?
Which one, the LBT or?
Euclid?
Euclid, yes. So there's a big problem with Euclid, is the sky background subtraction pipeline removes a lot of these data features.
I'm not so sure, but we can
Not
talk
so
about that
sure?
offline.
Okay, we can talk about that later. But yeah, of course, Euclid will be a very nice survey to study tidal features, yes.
Yeah. Okay, if there are any more questions, last questions. Thank you again, Helena, for a very nice talk.